Somewhere out there in the vast darkness of space, an invisible monster is whispering to us, not in words, not in light, but in signals so bizarre they defy everything we think we know about the universe. We call these cosmic enigmas black holes, but that name doesn't begin to capture their strangeness. These aren't just voids where matter vanishes. They're cosmic broadcasters, sending out mysterious pulses, unexplained echoes, and signals that ripple through space-time like a detective novel written in a language we're only starting to decipher. And the deeper we listen, the more questions they raise. Imagine tuning a radio and suddenly hearing a sound so powerful it rattles the speakers. A sound coming from a place where, by all known laws of physics, silence should reign. That's the paradox of black holes. They're supposed to be the ultimate endpoint, the universe's one-way doors, yet somehow they're blaring out signals that leave even the sharpest scientific minds utterly stumped. Some of these transmissions last mere milliseconds but pack the energy of 1,000 suns. Others repeat like clockwork, as if something or someone is hitting cosmic replay. And then there are the whispers, the faintest ripples in space-time that suggest black holes might be hiding secrets far stranger than we've dared to dream. Today, we're going on a journey to unravel 25 of these mind-bending signals, each one a cosmic breadcrumb leading us closer to the edge of understanding. Some will challenge Einstein's theories, others hint at dimensions beyond our own, and a few, well, they might just rewrite the rules of reality itself. This isn't just a tour of astronomical oddities, it's a detective story written across the fabric of the universe. So if you're ready to peer into the abyss and hear what it's trying to tell us, let's dive in. Because the deeper we go, the darker and more dazzling the mystery becomes. The story begins with a burst of radio waves so peculiar that astronomers scrawled, "Wow," in the margins of their data printouts, a single word that would immortalize one of the greatest cosmic mysteries. Detected in 1977 by Ohio State University's Big Ear telescope, this 72-second blip erupted from the constellation Sagittarius with a frequency eerily close to the hydrogen line, a natural marker scientists long considered the most likely channel for interstellar greetings. For decades, the WOW signal stood as the strongest candidate for extraterrestrial contact until black holes entered the conversation. Recent analysis reveals something even stranger. The signal's frequency and sudden drop-off match no known natural cosmic process except perhaps the death throes of matter spiraling into a black hole. Picture a dying star shredded by gravity's invisible fingers, its plasma stretched into a searing filament as it crosses the event horizon. In those final milliseconds, the collapsing matter could release a focused radio scream, brief, intense, and vanishing as abruptly as it appeared. What's baffling is that no black hole was known to exist in that region of space at the time, unless we missed one, or unless black holes can produce such signals in ways we don't yet understand. Then there's the signal's narrowband purity, like a laser beam cutting through cosmic static. Natural phenomena tend to broadcast across a range of frequencies, yet this transmission was surgically precise. Some theorists suggest it might have been amplified by an intervening black hole's gravitational lens, bending and focusing stray radio waves into that infamous spike. Others propose stranger ideas, microscopic primordial black holes evaporating in bursts of Hawking radiation, or even echoes from a parallel universe's collision with our own. One thing's certain: after nearly 5 decades, the WOW signal refuses to surrender its secrets, and with black holes now in the mix, the mystery only deepens. Deep in the heart of our Milky Way, where stars orbit an invisible titan, Sagittarius A unleashes bursts of radio energy so intense they flicker like a cosmic strobe light. These aren't your average radio emissions, they're millisecond-long firecrackers of radiation, each packing more energy than the sun releases in days. What makes them truly baffling isn't just their power, but their randomness. Unlike pulsars with their metronome-like precision, these fast radio bursts erupt without warning, sometimes in clusters, other times in eerie solitude, as if the black hole itself is tapping out a Morse code we can't decipher. Take the event catalogued as FRB 2020-24-0714. In less than 1,000th of a second, it flooded telescopes with radio waves so bright they drowned out background noise from the entire galactic core. Yet when scientists scrambled to study its aftermath, they found nothing. No lingering heat, no debris field, no telltale swirl of matter that usually accompanies black hole activity. It's like hearing a gunshot in an empty room. The sound is there, but the bullets vanished. Theories abound, each stranger than the last. One suggests these bursts could be the death screams of asteroids torn apart by the black hole's tidal forces, their fragments vaporizing into plasma that briefly conducts electricity like a cosmic spark plug. Another proposes that Sagittarius A's magnetic field, twisted into knots by the black hole's spin, might suddenly snap like an over-tensioned rubber band, releasing pent-up energy in these explosive ripples. Then there's the wild card, quantum effects near the event horizon, where particles popping in and out of existence might trigger runaway energy cascades. But here's the twist. Some of these bursts arrive with a peculiar double echo, a faint second pulse trailing the main burst by microseconds. That delay matches calculations for signals bouncing off an unseen structure just outside the event horizon, perhaps a dense shroud of dark matter or a previously unknown type of accretion disk. It's as if we're hearing not just the black hole's voice, but its echo in a hall of cosmic mirrors. With every new detection, Sagittarius A reminds us that the darkest corners of space still hold surprises waiting to rewrite the textbooks. 600 million light-years from Earth, a black hole is keeping time. Not with the erratic flickers we've come to expect from these cosmic beasts, but with a steady, rhythmic pulse, an X-ray heartbeat echoing across the universe with clockwork precision. Discovered in 2007, this bizarre signal from galaxy GSN 069 repeats every hour like a celestial metronome, flaring bright before fading to near silence, only to surge again right on schedule. It's the last thing astronomers expected from an object notorious for tearing apart the very fabric of predictability. The source, a supermassive black hole devouring a star trapped in its gravitational grip. Normally, such feasts are messy affairs with matter spiraling inward in chaotic bursts, but this black hole seems to be dining with unnatural restraint. As gas from the doomed star slides toward the event horizon, it heats up to millions of degrees, blasting out X-rays. Yet instead of a continuous scream, the emissions stutter like a stuck record, rising and falling with eerie consistency. It's as if some cosmic dam periodically opens and closes, regulating the flow of doomed matter into the abyss. What's truly baffling is the scale. These aren't subtle fluctuations. The X-ray output swings by a factor of 50, vanishing almost entirely before roaring back. One explanation suggests the black hole's magnetic field might be acting like a cosmic valve, alternately trapping and releasing matter in cyclical bursts. Others propose a more unsettling idea, that we're witnessing a resonance effect where the very fabric of space-time around the black hole vibrates at a specific frequency, like a plucked guitar string singing in perfect time. Then there's the endurance. Most tidal disruption events where stars are shredded by black holes fade within months. But this heartbeat has persisted for over a decade, defying models of how black holes consume their meals. Some theorists whisper of an undead star, a white dwarf caught in an eternal dance just outside the event horizon, its material slowly peeling away in measured portions. Others wonder if we're seeing evidence of a hidden partner, a second black hole locked in orbit, its gravity tugging the disk of debris like an unseen hand on a pendulum. The implications ripple far beyond this single anomaly. If black holes can produce such precise rhythms naturally, it could rewrite how we interpret other periodic signals from the cosmos, including those once chalked up to alien megastructures. Or perhaps this heartbeat is a rare glimpse of order emerging from chaos, a cosmic drumbeat hinting at laws of physics we've yet to uncover. One thing's certain, in the darkness of GSN 069, something is keeping time. And with every pulse, it challenges our understanding of how black holes and the universe itself truly work. In 2015, a sleeping giant woke screaming, and its voice echoed across the cosmos. The black hole V404 Cygni, normally quiet enough to escape notice, suddenly became the brightest object in the gamma-ray sky, firing off pulses of radiation so intense they temporarily blinded orbiting telescopes. But the real mystery wasn't just the eruption itself, it was what happened next. Each gamma-ray flare came back, not once but multiple times, like a shout bouncing between unseen canyon walls with delays that made absolutely no sense. Picture this, a blast of high-energy light erupts from the black hole's accretion disk, where superheated gas spirals toward oblivion. According to textbook physics, that energy should race straight toward us at light speed. Instead, telescopes detected identical flares reappearing minutes to hours later, some weaker, some distorted, as if the universe itself had hit pause and then replay. The effect was so pronounced that astronomers dubbed it the echo chamber hypothesis, suggesting something in the black hole's vicinity was catching these gamma rays and tossing them back into space like cosmic boomerangs. The leading theory points to an invisible structure, a dense, donut-shaped cloud of cold gas and dust surrounding the black hole at a distance of about 10,000 astronomical units. When gamma rays slam into this material, they might scatter like light through fog, some photons taking detours before eventually reaching our telescopes. But here's the catch: the echoes didn't arrive in neat, predictable intervals. Some came staggered, others overlapping, as if multiple unseen surfaces were playing pinball with the radiation. Even stranger, a few flares seemed to split into twin echoes, implying something far more complex than a simple dusty ring. Perhaps warped space-time itself bending the paths of these photons into knots. Then there's the energy problem. Gamma rays pack enough punch to blast through most obstacles, yet these echoes retained startling clarity, as if whatever reflected them was both dense enough to bounce back high-energy photons and yet transparent enough not to absorb them completely. It's like hearing an opera singer's voice echo through solid stone. The physics just doesn't add up. Some researchers speculate that magnetic fields near the black hole could be corralling particles into mirrored surfaces, while others wonder if we're seeing evidence of quantum gravity effects, where space-time behaves less like a smooth fabric and more like a frothy sea at microscopic scales. The most unsettling possibility: these echoes might be our first glimpse of a black hole's ergosphere, a region just outside the event horizon where space-time gets dragged around the spinning singularity like water in a whirlpool. Photons entering this zone could get slingshot in bizarre trajectories before escaping, creating delayed, distorted copies of the original signal. If true, V404 Cygni isn't just screaming into the void, it's singing in rounds, with the universe itself harmonizing in ways we're only beginning to decipher. And with every echo, it reminds us that black holes don't just consume light, they can twist it, stall it, and send it back to us wearing masks we barely recognize. GSN 069 doesn't just scream, it does so on a schedule precise enough to set your watch by. Every 9 hours, like clockwork, this supermassive black hole unleashes an X-ray flare so intense it outshines its entire galaxy, then falls silent again as if someone flipped a cosmic switch. What makes these eruptions extraordinary isn't just their regularity, but their sheer violence. Temperatures spike to hundreds of millions of degrees in minutes, then plummet just as fast, a thermal roller coaster defying all expectations of how black holes feed. The culprit, a star caught in the black hole's gravitational claws, slowly being peeled apart layer by layer. But here's where normal physics ends and the mystery begins. Most tidal disruption events where black holes rip stars to shreds create chaotic, unpredictable bursts of radiation. GSN 069's emissions, however, follow a rhythmic pattern so exact it resembles a celestial metronome. It's as if the black hole is digesting its meal with deliberate, measured bites rather than the usual cosmic gluttony. One explanation lies in the accretion disk's bizarre behavior. Normally, gas orbiting a black hole heats up unevenly, creating turbulent, continuous radiation. But simulations suggest this disk might be caught in a feedback loop. When too much material piles up near the event horizon, the resulting X-ray flare blows away surrounding gas like a cosmic leaf blower. The disk then cools and collapses, only to rebuild until the cycle repeats 9 hours later like clockwork. Think of it as a pressure valve on a boiling kettle, releasing steam in perfect intervals. Yet even this doesn't fully explain the signal's purity. Some theorists propose a more exotic scenario: quantum effects near the event horizon creating resonant vibrations, or even gravitational waves ricocheting through the disk like a struck gong. Others wonder if we're witnessing a rare limit cycle, where competing forces, gravity, magnetism, and radiation pressure balance so precisely they create a natural oscillator. Then there's the star itself. Most tidal disruptions involve sun-like stars torn apart in months. But if GSN 069's victim is a dense white dwarf, its sturdy core might resist complete destruction, orbiting just outside the event horizon and shedding material in regular outbursts. Imagine an apple on a string, swung in circles while a knife shaves off slices, with each pass a grisly metaphor, but one that fits the data. The implications ripple far beyond this single system. If such clockwork flares prove common, they could revolutionize how we measure cosmic distances or even test Einstein's theories under extreme gravity. But for now, GSN 069 remains an enigma, a black hole that doesn't just devour, but does so with a precision that feels almost intentional. As if somewhere in those 9-hour intervals, the universe is whispering a secret we've yet to fully hear. The universe sent us a love letter written in the language of gravity, and we still can't decipher its meaning. On May 21, 2019, gravitational wave detectors caught something impossible. A space-time ripple catalogued as GW 190521, born from a collision so violent it briefly outshone every star in the observable universe combined. But here's what rattled scientists: the numbers didn't add up. This wasn't just another black hole merger, it was a cosmic magic trick defying every expected law of physics. First, the scale. 2 monsters, one 85 times the mass of our Sun. The other 66 came crashing together, birthing a final black hole weighing in at a staggering 142 solar masses. That middle number is critical because it lands squarely in the pair instability gap, a mass range where stars aren't supposed to collapse into black holes at all. According to stellar evolution models, stars between 65 and 130 solar masses should self-destruct in thermonuclear explosions so complete they leave nothing behind. Yet here we are, staring at the fingerprints of 2 black holes that by all rights shouldn't exist. Then there's the spin. Most black holes rotate like spinning tops, their angular momentum imprinted from their starry origins. But the remnants of GW 190521 were practically stationary, as if the colliding objects had no spin whatsoever. This oddity points to formation channels we've never observed, perhaps black holes born not from dying stars, but from the direct collapse of primordial gas clouds in the early universe. Or something even stranger, enter the wildcards. One tantalizing theory suggests these might be primordial black holes, hypothetical relics from the universe's first microseconds. Unlike their stellar-born cousins, these would form from dense fluctuations in the newborn cosmos, potentially explaining their unusual masses and lack of spin. Others float an even more exotic possibility: cosmic strings, hypothetical defects in space-time thinner than a proton but stretching across galaxies. If two such strings crossed, their interaction could theoretically mimic a black hole merger's gravitational waves without any actual black holes involved. The collision setting deepens the mystery. Unlike most gravitational wave events traced to active star-forming regions, this echo came from a cosmic void, a patch of space nearly 2 billion light-years away where galaxies are scarce. Such emptiness makes stellar origin black holes statistically unlikely, fueling speculation about dark matter's role. Could these invisible giants be the missing dark matter astronomers have hunted for decades? Then there's the afterglow, or rather, the lack of one. Mergers usually produce a faint electromagnetic signature as surrounding gas gets heated, but follow-up observations found nothing. This silence feeds theories about dark mergers, where black holes collide without the usual cosmic fanfare, perhaps in environments stripped clean of gas by previous encounters. The implications are staggering. If primordial black holes exist, they could rewrite cosmic history, potentially solving mysteries from dark matter to galaxy formation. Cosmic strings, if confirmed, would offer proof of theories predicting extra dimensions beyond our four-dimensional space-time. Even the mundane explanation that we've fundamentally misunderstood stellar evolution would send shockwaves through astrophysics. GW 190521 feels less like a singular event and more like a Rosetta Stone for the cosmos, its hieroglyphs etched not in stone but in the fabric of reality itself. With each new analysis, it whispers the same unsettling truth. Black holes might be the universe's way of reminding us how much we still have left to learn. And the next ripple in space-time could arrive any moment, carrying secrets we're not even equipped to imagine yet. When scientists unveiled humanity's first ever image of a black hole in 2019, one feature stole the spotlight: the colossal jet of plasma erupting from M87's supermassive heart, stretching 5,000 light-years into space like a cosmic blowtorch. This jet, visible across multiple wavelengths, seemed as permanent as the galaxy itself until it vanished. By 2021, telescopes trained on M87 showed nothing but eerie silence where that fiery beam should have been. The disappearance wasn't just unexpected, it defied decades of astrophysical dogma. Black hole jets aren't supposed to flicker out like candle flames. They're thought to be powered by the very rotation of space-time itself, a process so relentless it should last for millennia. Yet M87's jet didn't dim gradually, it blinked off like a switched-off flashlight. Theories immediately split into two camps. The first suggests we're witnessing a cosmic sleight of hand, an illusion caused by shifting shadows in the black hole's accretion disk. Just as clouds can obscure the sun while it still burns, dense knots of gas might be passing between the jet and our telescopes, blocking our view. Supporting this, some radio observations detected faint hints of the jet's base still churning, hinting the engine hadn't stopped but merely cloaked itself. Yet even this explanation raises questions. For the jet to vanish so completely, the obscuring material would need unprecedented density, or the jet's angle might have abruptly shifted, a phenomenon never before observed in such a stable system. The second camp argues something far more radical. The black hole's magnetic field underwent a spontaneous reboot. Jets form when twisted magnetic fields near the event horizon funnel matter outward at near light speeds. If those fields suddenly collapsed, perhaps due to an instability in the accretion disk, the jet could dissipate almost instantly. There's precedent in smaller black holes, where magnetic reconnection events caused temporary jet disruptions, but nothing on this scale. The energy budget alone boggles the mind. M87's jet carried enough power to outshine entire galaxies. meaning any process capable of halting it would release unfathomable shockwaves through the surrounding space-time. Yet the most tantalizing clue lies in the timing. The jet's disappearance coincided with a subtle but measurable change in the black hole's shadow. The dark center of its iconic image appeared slightly more elongated in 2021. This could imply the accretion disk tilted, altering our perspective on the jet's structure. Alternatively, it might signal the onset of a magnetically arrested disk, a rare state where inward-flowing matter temporarily overwhelms the black hole's magnetic field lines, starving the jet. Then there's the wild card, black hole recoil. If M87 recently merged with another supermassive black hole, a possibility given its galaxy's violent merger history, the resulting gravitational kick could have jostled the accretion disk like a bump to a record player, disrupting the jet's delicate launch mechanism. While no direct evidence supports this yet, it would explain both the suddenness of the jet's collapse and the shadow's distortion. Whatever the cause, M87's vanishing act forces us to confront an uncomfortable truth. Black holes might be far more temperamental than we ever imagined. These aren't just predictable gravity wells, they're dynamic engines capable of abrupt shifts that rewrite the rules of cosmic behavior. And with the jet now showing tentative signs of reawakening as of 2023, its full story remains half told, a reminder that even our most iconic celestial portraits capture just a fleeting moment in a much longer, stranger saga. On August 17, 2017, the universe handed scientists a Rosetta Stone written in light, gravity, and fire. That day, gravitational wave detectors and telescopes worldwide caught the first ever cosmic tango of two neutron stars, an event dubbed GRB 170817A. The collision sent ripples through space-time and blasted out a short gamma-ray burst, one of the most energetic phenomena known. But the real surprise came afterward, when the fading afterglow of that explosion did something impossible. It got brighter. Normally, neutron star merger afterglows follow a predictable decay like embers cooling after a fireworks burst. Yet here, the visible and X-ray light rebounded days later, glowing with renewed intensity long after the initial crash. It was as if someone had poured gasoline on those embers, defying all models of how such events should behave. The leading explanation, a hidden black hole born from the wreckage of those colliding stars, might have begun feeding on the surrounding debris, a cosmic phoenix rising from its own ashes. The numbers told the story. To reach that level of brightness, the afterglow required an energy source far beyond what a typical debris field could provide. Simulations pointed to a central engine, likely a newborn black hole, injecting fresh energy into the system. As this invisible predator consumed stray matter, its magnetic fields could have funneled material into powerful jets, reigniting the afterglow like a dying bulb suddenly surging with voltage. But the plot thickened. The rebrightening didn't follow the smooth curve expected from a simple black hole snack. Instead, the light curve jerked and sputtered, suggesting chaotic feeding behavior. Some theorists proposed the black hole might be struggling to swallow a particularly stubborn piece of debris, perhaps a fragment of the original neutron stars that survived the initial collision. Others wondered if we were seeing the birth throes of an accretion disk, its magnetic fields tangling and reconnecting in fits and starts. Then there's the wildest possibility, that the collision didn't produce just any black hole but a magnetar, a highly magnetized neutron star briefly spinning at impossible speeds before collapsing into the abyss. Such an object could have pumped energy into the surrounding wreckage like a cosmic defibrillator, explaining the afterglow's erratic pulse. Yet even this theory fails to fully account for the signal's duration, leaving room for even stranger explanations. What makes GRB 170817 so tantalizing isn't just the anomaly itself, but what it reveals about the messy physics of stellar death. Neutron star mergers were thought to be relatively clean events, their afterglows fading predictably as expanding debris cools. This orphaned afterglow suggests something far more dynamic, a battlefield where gravity, magnetism, and quantum forces wrestle in real time. It's a reminder that even our best models are just sketches of a reality far richer and far stranger than we've dared to imagine. And with every similar event detected since, each with its own peculiar twists, the message grows clearer. When neutron stars collide, they don't just fade quietly into the night. Sometimes they leave behind monsters we're only beginning to understand. Some black holes announce their presence with a roar. OJ-287 prefers a cosmic game of hide and seek. Nestled 3.5 billion light-years away in the constellation Cancer, this supermassive binary doesn't just defy expectations, it toys with them. Every 12 years, like clockwork, astronomers brace for twin flares brighter than a trillion suns' light shows caused by the smaller black hole plunging through its massive partner's accretion disk. But here's the catch: sometimes these fireworks arrive right on schedule, and sometimes they ghost us entirely, vanishing like a magician's trick. The last no-show in 2019 left telescopes staring at empty sky, as if physics itself had rewritten the rules. What makes OJ-287 so baffling isn't just its unpredictability, it's the precision of its chaos. General relativity predicts these flares to within 4 hours when they do appear, a testament to Einstein's enduring genius. Yet the system's refusal to perform on command reveals cracks in our understanding. The smaller black hole's orbit isn't a neat ellipse but a spirograph scribble, warped by each near-light-speed plunge through the disk. Imagine a motorboat circling a whirlpool, its path bending unpredictably as it slices through frothing water. That's the dance happening here, with space-time itself as the turbulent medium. The missing flares might hold the key to even deeper mysteries. One theory suggests the smaller black hole's gravity could be warping the disk into temporary shadow zones, redirecting energy away from our line of sight. Another proposes that magnetic field lines, stretched like rubber bands during close passes, might snap and realign moments before impact, choking off the expected radiation burst. Then there's the wild card: quantum friction between the disk and the intruding black hole, a phenomenon so poorly understood it might as well be magic. Yet OJ-287's greatest gift is how it tests relativity under extreme conditions. Each erratic flare, or lack thereof, carries fingerprints of gravitational radiation, frame dragging, and other subtle effects predicted but rarely observed. The binary's 12-year tempo also serves as a natural laboratory for studying how supermassive black holes grow through mergers. If we can crack its code, we might finally understand why some cosmic giants refuse to play by the rules, and what their tantrums reveal about the fabric of reality itself. For now, astronomers keep watching, knowing the next flare could arrive right on time, or not at all. And in that uncertainty lies the thrill, because OJ-287 isn't just a black hole binary. It's a cosmic chess game where every move teaches us something new, and the universe always holds the winning strategy. On June 14, 2019, gravitational wave detectors picked up a whisper from the Voyager W190814. At first glance, it seemed like just another cosmic collision. A black hole 23 times the sun's mass swallowing something smaller, but the numbers didn't add up. That something weighed 2.6 solar masses, an impossible weight for known physics. Too hefty to be a neutron star, yet too featherlight for a textbook black hole. It was like finding a door that was neither open nor closed, but stuck somewhere in between. This cosmic Goldilocks object sent theorists scrambling. Neutron stars, those ultra-dense remnants of dead stars, should collapse into black holes before reaching 2.2 solar masses. Yet here was an entity defying that limit, surviving where it had no right to. Some proposed it might be an unusually hefty neutron star, squeezed just shy of collapse by exotic quantum forces. Others wondered if we'd stumbled upon a black neutron star, an object caught mid-transformation, its core already crushed into a singularity while its outer layers clung to degeneracy pressure like a drowning swimmer grasping at foam. The most tantalizing possibility, a quark star. These hypothetical oddities could form when neutron star matter fractures under pressure, their protons and neutrons dissolving into a soup of free-floating quarks. Such an object might temporarily stabilize between neutron star and black hole states, existing in a quantum purgatory that would rewrite our understanding of dense matter. Imagine a diamond compressed until its atomic structure shatters, becoming something entirely new, neither crystal nor liquid, but a substance obeying rules we've yet to name. Then there's the merger itself. Unlike most gravitational wave events which roar like thunder, GW190814 arrived as a faint murmur. The signal's quietness suggests the smaller object might have been swallowed whole, vanishing without the usual accretion disk fireworks. This quiet death hints at an ultra-compact structure, perhaps a black hole so young its event horizon hadn't fully formed, or a neutron star wrapped in an invisible cloak of dark matter, suppressing electromagnetic emissions. The implications ripple outward. If such intermediate mass objects exist, they could be the missing link in black hole formation, bridging the gap between stellar corpses and supermassive giants. Or they might represent an entirely new class of celestial bodies, lurking undetected throughout the cosmos. Every time our instruments listen harder, the universe seems to mock our categories, revealing objects that refuse to fit neatly into boxes. GW190814 isn't just a puzzle. It's a siren call from the dark, luring us toward frontiers where even our best theories dissolve into wonder. Maxi J1820 plus 070 doesn't just flicker. It plays cosmic peekaboo with X-rays. In 2018, astronomers watching this black hole 12,000 light-years away witnessed something bizarre. Its X-ray emissions didn't just dim gradually or flare unpredictably. They dropped out completely, plunging to near zero levels in minutes before snapping back to full brightness like a switch being flipped. These weren't the gentle dips of a dying star or the rhythmic pulses of a feeding black hole. They were sudden, total blackouts, as if the universe itself had blinked. The culprit, a warped accretion disk dancing like a ribbon in the wind. Most black holes feed from flat, orderly disks of gas, but Maxi disk is anything but stable. Simulations suggest it might be twisted into a lopsided shape by the black hole's extreme gravity, wobbling like a spinning top as it orbits. When the warped portion swings edge onto our line of sight, it could momentarily block our view of the inner disk's X-ray glow. Imagine holding a flickering candle behind a spinning vinyl record. When the record tilts just right, the flame vanishes completely. But here's where things get interesting. The dips happen too fast for simple obscuration. One study clocked the transitions at under 90 seconds, far quicker than any known disk structure could rotate into place. That speed implies something far stranger. A light echo effect where X-rays emitted near the event horizon get bent around the black hole's gravitational whirlpool, taking detours before reaching us. When those detoured photons arrive out of sync with the direct beam, they cancel each other out like waves colliding in a pond. Then there's the energy signature. Unlike typical absorption dips where higher energy X-rays punch through while softer ones fade, Maxi blackouts hit all wavelengths equally. This points to a geometric shadow rather than a physical barrier, as if space-time itself were the curtain being drawn. Some theorists speculate we might be seeing the shadow of the black hole's ergosphere, the region where space gets dragged around the spinning singularity like taffy. Matter orbiting here could act like a funhouse mirror, bending light paths so severely that the inner disk periodically winks from view. Alternative explanations push the boundaries of known physics. One radical idea involves magnetically elevated disk patches, dense knots of plasma held aloft by magnetic fields above the disk surface, casting moving shadows like clouds over the sun. Another proposes sudden evaporations of the innermost disk, where quantum effects near the event horizon cause chunks of material to vanish before reaching the point of no return. It's as if the black hole keeps spitting out its meal at the last second, leaving us staring at an empty plate. The most tantalizing clue lies in the timing. These dips tend to cluster in active periods, then vanish for months, a pattern suggesting the disk's warp might be driven by some hidden resonance. Perhaps the smaller companion star feeding the black hole tugs on the disk at precise intervals, or the black hole's spin precesses like a wobbly gyroscope, periodically aligning the warp to block our view. Whatever the cause, Maxi J1820 plus 070 offers a rare glimpse into the chaotic ballet of matter at gravity's edge. Most black holes hide their feeding mechanisms behind veils of plasma and distance, but this one's X-ray teasers lay bare the violence and beauty of a disk pushed to its limits. With every dip and recovery, it whispers the same truth. Even in the darkest corners of space, light finds ways to surprise us. And sometimes the most revealing moments aren't when a black hole shines, but when it chooses to hide. Most black holes announce their presence with X-ray screams or radio blasts. Assassin 14, LIGO's infrared whispers. When this supermassive black hole tore apart a passing star in 2014, telescopes expected the usual fireworks, ultraviolet flares from superheated debris, maybe some X-rays from the accretion disk's inner edge. Instead, they found something far stranger, a persistent infrared glow that grew brighter for months after the initial explosion, as if someone had left a cosmic radiator running in the darkness. This wasn't just residual heat. The infrared emission followed a curve too steady for random debris cooling, and its spectrum carried the chemical fingerprints of silicate dust, a material that shouldn't survive so close to a black hole's destructive forces. It was like finding frost clinging to a blast furnace. The leading explanation, a hidden structure, perhaps a lopsided disk of stellar debris, tilted just right to radiate infrared while shielding its dust from the black hole's worst fury. Imagine a hurricane's eye wall where chaos meets eerie calm, except here the calm zone is a ring of surviving stardust orbiting mere light hours from the event horizon. Yet the infrared glow held another clue: polarization. When astronomers measured how the light waves aligned, they found patterns suggesting more than just passive dust. Something was sculpting that emission, possibly a faint jet of particles punching through the debris field. Most jets announce themselves with bright radio lobes, but this one might have been too quiet for traditional detection. Its energy diverted into heating surrounding dust like a ghostly hand warming a pane of glass. Alternative theories push the boundaries of known physics. One suggests we're seeing echoes from a failed jet, a choked-off outflow that never fully escaped the black hole's grasp, instead dumping its energy into a cocoon of shocked material. Another proposes quantum friction between fast-moving debris and the black hole's magnetosphere, generating infrared as a byproduct of space-time itself being stirred. The most tantalizing possibility involves dark matter. If certain hypothetical particles cluster near black holes, their collisions could produce infrared signals matching Assassin 14's glow. It's a long shot, but when conventional physics falls short, the universe often whispers its secrets through the cracks. What makes this signal so transformative isn't just the anomaly itself, but what it reveals about black holes' hidden ecosystems. We've long assumed tidal disruptions were one-shot fireworks. A star enters, detonates, and vanishes. Assassin 14's lingering infrared embrace suggests these events might birth entire temporary architectures, dust rings, stifled jets, or even new forms of accretion we've yet to name. It's a reminder that even in destruction, black holes create, and sometimes the most revealing light arrives not in a flash, but as a slow, warm glow from the dark. The first gravitational waves ever detected didn't just ripple through space-time, they sang. When LIGO instruments caught GW 150914 in 2015, the signal burst forth not as a silent tremor, but as a rising crescendo scientists dubbed the chirp. In milliseconds, its frequency soared from 35 to 250 Hz, a cosmic slide whistle capturing the final death spiral of two black holes colliding. But buried in that iconic sound lay something even stranger, faint harmonic overtones, echoes within echoes that shouldn't exist if black holes are as bald as Einstein predicted. According to general relativity, black holes should be the universe's simplest objects defined only by mass, spin, and charge, with no other distinguishing features. This no-hair theorem suggests all other details get erased at the event horizon, like letters written in steam. Yet GW150914's overtones hint at subtle deviations, as if space-time itself carried faint brushstrokes from the black hole's violent past. Imagine dropping two pebbles into a pond and seeing not just concentric circles, but tiny ripples within ripples preserving the shape of each stone. That's the tantalizing possibility these gravitational wave harmonics suggest. The math reveals why this matters. When black holes merge, the newborn singularity doesn't immediately settle into silence. It rings down, vibrating like a struck bell at specific frequencies called quasi-normal modes. The loudest tone corresponds to the black hole's fundamental pitch, but the overtone's higher, fainter frequencies should theoretically decay too fast to detect. Yet in GW150914, certain overtones persisted longer than models predicted, as if the black hole's surface or what passes for one held onto some hidden texture. Some theorists believe these anomalies could point to quantum hair, microscopic structures at the event horizon imprinting themselves on gravitational waves. Others propose that the pre-merger black holes might have carried faint memory of the stars they once were, not in material form, but encoded in warps of space-time itself. Then there's the wild card, extra dimensions. If gravity leaks into higher dimensions as some string theory models suggest, the chirp's overtones could carry fingerprints of that hidden geometry. The implications are staggering. If black holes do have hair, even of the quantum variety, it would upend decades of astrophysical dogma. Suddenly, these cosmic voids might preserve information about what falls in, a potential solution to the infamous black hole information paradox. It could also give us a new tool to probe gravity's extremes, using mergers as natural laboratories to test theories beyond Einstein's framework. GW150914's chirp was just the beginning. As detectors grow more sensitive, future observations might catch these harmonic whispers clearly enough to decode their meaning. Until then, that first signal remains a cosmic riddle wrapped in space-time, vibrating with secrets we've only begun to hear. Cygnus X1 has always been a show-off among black holes. The first ever confirmed, the closest stellar mass black hole we've found, and now the one that's twisting light into cosmic riddles. In 2021, astronomers pointed NASA's Imaging X-ray Polarimetry Explorer at this legendary object and got back something unexpected. X-rays with a peculiar polarization signature, their electric fields aligned in ways that shouldn't happen near a normal black hole. The signal suggests space itself might be corkscrewing around Cygnus X1 like water swirling down a drain, imprinting its chaos on every photon that escapes. The key lies in the angle. Polarized light from typical black holes aligns neatly with their jet's powerful beams of particles launched along the spin axis. But Cygnus X1's X-rays arrived twisted nearly 90 degrees off kilter, as if the black hole's gravity had wrung them through an invisible cosmic mangle. One explanation points to a misaligned accretion disk where superheated gas orbits at a steep angle to the black hole's spin. As X-rays generated near the event horizon try to escape, they'd have to plow through this lopsided disk, scattering off electrons that effectively comb the light's polarization in unexpected directions. Imagine sunlight filtering through a window blind, except the slats aren't straight but bent like a roller coaster track. But there's a wilder possibility, frame dragging so extreme it warps the very fabric of space-time. Einstein predicted spinning black holes would drag nearby space around with them like a spoon stirring honey, near Cygnus X1, which rotates at over 800 times per second. This effect could be strong enough to twist magnetic field lines into knots, forcing escaping X-rays to corkscrew along curved paths. The resulting polarization pattern would be a fingerprint of space-time itself in turmoil, a direct glimpse of relativity in overdrive. Then there's the jet's role, or rather, its absence. Most models assume black hole jets form perpendicular to their accretion disks. Yet Cygnus X1's jet seems to wobble precariously, as if fighting against some unseen torque. The polarized X-rays might be tracing this instability, revealing moments when the jet flickers off axis, caught between the black hole's spin and the disk's stubborn tilt. Alternatively, we might be seeing evidence of a failed jet, a choked-off outflow that never fully escapes the black hole's grasp, spraying X-rays sideways like a garden hose with a kink. The most tantalizing clue comes from timing. The polarization angle shifts slightly during Cygnus X1's X-ray flares, subtle changes that align with predictions of how a warped disk might precess under extreme gravity. It's as if we're watching a cosmic gyroscope wobble in slow motion, each oscillation tweaking the light's journey. If confirmed, this would mark the first time we've observed dynamic frame dragging imprinting itself on electromagnetic radiation, turning Cygnus X1 into a natural laboratory for testing gravity's limits. What makes this signal revolutionary isn't just the weirdness, it's the precision. For decades, studying black hole spin relied on indirect methods like measuring X-ray flickers or jet speeds. Polarization hands us a direct probe, a way to map the maelstrom right at the event horizon's edge. And with Cygnus X1's twisted light as our guide, we're one step closer to answering a haunting question. When a black hole spins, does space-time merely bend, or does it break into something stranger than we've dared to dream? NGC 4151 doesn't just flicker. It leaves fingerprints. This active galaxy, 38 million light-years away, has long been known for its brilliant core, a telltale sign of a supermassive black hole devouring matter. But in 2022, astronomers noticed something bizarre. Its X-ray emissions weren't just fluctuating randomly. They were bouncing off invisible walls in deep space, creating a celestial echo chamber that mapped hidden structures around the black hole with startling precision. These light echoes work like cosmic sonar. When the black hole's core flares, X-rays blast outward in all directions. Most race straight to our telescopes, but some hit intervening clouds of gas, scattering in our direction milliseconds to years later. By tracking these delayed photons, researchers assembled a 3D map of the black hole's surroundings and uncovered a strobe-like flicker at the heart of the chaos. The pattern suggests the black hole isn't feeding smoothly, but in rapid bursts, as if something is clenching and unclenching around its maw, the prime suspect. A shroud of clumpy gas clouds orbiting perilously close to the event horizon. Most active galaxies have relatively smooth accretion disks, but NGC 4151's echoes imply a turbulent, fragmented environment. Picture a bonfire flickering behind a sheet of frosted glass, except the glass is a swarm of planetary-scale gas blobs, each distorting the light in its own way. Some models suggest these clouds could be survivors of shredded stars, their debris not fully assimilated into the disk. Others propose their evidence of a failed wind, where material blown outward by the black hole's radiation gets trapped in gravitational eddies, condensing into dense knots. But there's a twist. The echoes show delays inconsistent with simple orbital mechanics. Some X-rays arrive too early, others too late, as if space-time itself is warped around the black hole in ways we can't yet model. This has sparked debates about whether we're seeing gas clouds at all, or something far stranger like floating islands of dark matter or even quantum fluctuations in the fabric of space magnified to macroscopic scales. The most tantalizing clue lies in the echospectral fingerprints. Certain energy bands fade faster than others, hinting that the obscuring material isn't just cold gas, but plasma threaded with magnetic fields. These fields could be redirecting X-rays like a hall of mirrors, creating echo patterns that fool us into seeing structures where none exist. Alternatively, the black hole's own magnetic field might be rippling its accretion disk into peaks and troughs, casting moving shadows that masquerade as physical clouds. What makes NGC 4151's echo map revolutionary isn't just the hidden structures it reveals, it's the timeline. By comparing echoes from flares decades apart, astronomers have caught the black hole's neighborhood in motion, watching as clouds shift and the flicker pattern evolves. It's like finding a cosmic flipbook buried in the static of deep space, each page offering a clearer view of how black holes sculpt their surroundings. And with every new echo, this cryptic strobe light in the void reminds us, even the darkest corners of the universe can't hide forever when we learn to listen to their reflections. Most black holes fire their jets like cosmic rifles, straight and true. H174332 prefers a drunken stumble. Located 28,000 light-years away in Scorpius, this black hole's plasma jet doesn't just flicker or fade, it writhes like a snake in midair, twisting through space at angles that change by the week. Some days it points due north, others it veers 40 degrees off course without warning. It's the astrophysical equivalent of a compass needle spinning wildly, and the culprit might be space-time itself throwing a tantrum. The leading theory involves a warped accretion disk caught in a gravitational tug-of-war. Unlike the orderly, flat disks seen around most black holes, H174332's feeding zone appears lopsided, wobbling as it orbits like a vinyl record left too close to a heat source. As the disk processes, its magnetic field lines, which normally channel jets into straight beams, get twisted into spirals, forcing the jet to corkscrew erratically. Imagine trying to drink from a hose while someone shakes the nozzle. That's the chaos unfolding here, except the someone is the black hole's own extreme gravity warping the rules. But there's a stranger possibility, frame dragging gone rogue. Einstein predicted spinning black holes should drag space-time around them like molasses on a spoon. In extreme cases, this could torque the inner accretion disk into misalignment with the black hole's equator, creating a feedback loop where the jet's own momentum further destabilizes its launch path. Recent radio observations caught the jet bending clockwise over 6 months, a motion matching simulations of a black hole spinning at near light speed, its ergosphere yanking the disk sideways with each rotation. Then there's the wild card hidden companions. Some astronomers speculate the jet's wobbles coincide with periodic dips in X-ray emissions, hinting at a second, smaller black hole or neutron star orbiting the main attractor. Every close pass could stir the accretion disk like a spoon in soup, redirecting the jet's trajectory. Supporting this, the system's X-ray bursts sometimes arrive in pairs, suggesting gravitational disturbances from an unseen partner. The most baffling feature, the jet's speed doesn't match its dance moves. Despite its erratic direction, the plasma still rockets outward at 90% light speed, proof that raw power doesn't guarantee stability. It's like watching an Olympic sprinter zigzag down the track without losing momentum, defying every law of inertia. What makes H174332 so revolutionary isn't just the spectacle, it's the clues hidden in its instability. Most jets serve as cosmic yardsticks, their straight paths helping astronomers measure distances across the universe. This one's drunken stagger forces us to question whether other, stable jets might have wobbled too subtly for us to notice. And with every unpredictable twist, it whispers a humbling truth. Even the mightiest forces in nature can lose their balance when space-time itself starts to spin out of control. At the heart of Galaxy CQ4479, a cosmic contradiction rages: a quasar burning bright enough to outshine entire galaxies, surrounded by a swirling reservoir of frigid gas that by all rights shouldn't exist. Discovered in 2019, this so-called cold quasar defies one of astronomy's most fundamental assumptions, that supermassive black holes, as they feast, must scorch their surroundings into oblivion. Instead, CQ4479 cradles enough icy molecular gas to forge 10 billion suns, all while its central black hole devours matter at a voracious pace. It's like finding a glacial lake nestled inside an active volcano, a phenomenon so unlikely that its discovery sent theorists back to their chalkboards. The mystery deepens when you examine the temperatures. Quasars, the brilliantly luminous cores of distant galaxies, are thought to sterilize their neighborhoods with fierce radiation and powerful jets, boiling away any unshielded gas. Yet observations from the SOFIA Airborne Telescope reveal CQ4479's cold gas hovers near -260 degrees Celsius, mere degrees above absolute zero. This surviving frost lingers less than 3,000 light-years from the quasar's fiery maw, shielded by some unseen cosmic umbrella. One clue lies in the gas's distribution. It's not spread evenly, but clumped into dense, rotating filaments like spiral arms within a spiral. These structures may act as refrigerated vaults, their sheer mass protecting inner layers from the quasar's heat, while their rotation prevents collapse into new stars. But here's the real puzzle. This frigid reservoir shouldn't just survive, it's actively growing. Spectroscopy shows fresh streams of cold gas funneling toward the galaxy's core even as the black hole feasts, a conveyor belt of star-forming fuel replenishing faster than radiation can destroy it. Some theorists propose dark matter's invisible hand at work, its gravitational scaffolding guiding intergalactic gas safely past the quasar's fury. Others point to the black hole's unique diet. It might be consuming matter in intermittent bursts, leaving lulls where cold gas can sneak through. The implications rewrite galactic life cycles. Conventional wisdom says quasars mark a galaxy's death throes, their radiation expelling gas and halting star birth in a process called quenching. CQ4479 flips this script. Its cold gas reserves suggest some black holes might actually prolong their host galaxy's star-forming youth, like a fire that somehow feeds the forest instead of consuming it. This could explain why massive galaxies in the early universe formed stars long after models predicted they should have gone dormant. Perhaps most tantalizing is what this means for black hole feedback, the delicate balance between a black hole's destructive power and its role in shaping galaxies. Instead of merely blowing away star-forming material, CQ4479's black hole might be sculpting its cold gas into structures ripe for future stellar nurseries. It's a cosmic paradox. The same force that can sterilize a galaxy might also, under the right conditions, set the table for its rebirth. And with new telescopes like JWST peering deeper into such enigmas, we're left to wonder, is this cold quasar a cosmic oddity, or have we been overlooking an entire chapter in the story of how galaxies live and die? ARP-102b doesn't just sing, it harmonizes with itself. Nestled 700 million light-years away in Hercules, this active galaxy emits a spectrum unlike any other. Twin peaks of hydrogen alpha light perfectly mirrored like a cosmic Rorschach test. Most supermassive black holes show a single, broad emission line as their accretion disks whirl at relativistic speeds. But ARP's double peak suggests something extraordinary. We might be staring directly down the throat of the beast, witnessing its disk from a vantage point so rare it rewrites the playbook on black hole observation. The secret lies in the Doppler effect. Normally, we see accretion disks edge on, where one side races toward us blue-shifting light, while the other recedes red-shifting light, smearing the emission into a single broad line. But if we peer directly face-on at the disk, like looking into a spinning record from above, gas on opposite sides moves perpendicular to our line of sight. The result, two distinct peaks, one from material swirling clockwise, the other counterclockwise, meeting at a precise wavelength where motion neither approaches nor retreats. It's the astrophysical equivalent of hearing a train whistle's pitch stay constant as it circles around you, yet ARP's symmetry hides deeper puzzles. The peaks aren't just cleanly split, they're offset, with one slightly brighter than the other. This imbalance hints at a disk that's not perfectly flat, but warped like a vinyl record left in the sun. One theory suggests the black hole's magnetic field could be distorting the inner disk, creating dense plasma clouds that shadow portions of the outflow. Another proposes we're seeing the aftermath of a recent stellar snack, where a shredded star's debris hasn't fully settled into orderly orbits. Then there's the forbidden middle dip. Standard models predict a sharp trough between the peaks where cooler gas absorbs some emission. Instead, ARP's spectrum shows a rounded valley, suggesting turbulent mixing between disk layers, or stranger still, a hollow region where the black hole's gravity prevents stable orbits, carving a gap in the emission like a skipped groove on a record. The most tantalizing clue comes from variability. Over decades, the peaks have subtly shifted wavelengths, as if the disk itself is wobbling like a spinning top losing momentum. This could signal an unseen companion black hole tugging on the disk, or perhaps the disk processing under its own extreme physics. Whatever the cause, ARP-102b's twin voices are singing a duet we've only begun to understand. A rare front row seat to the chaotic ballet where gravity and light perform their most intricate pas de deux. TXS 0506 plus 056 should be just another blazar, a supermassive black hole firing a jet straight at Earth, its light amplified by relativistic effects. But in 2017, this cosmic spotlight did something unprecedented. It shot a neutrino through our planet that Ice Cube's detectors in Antarctica caught like a cosmic bullet. That subatomic particle, traveling nearly unimpeded for 4 billion light-years, marked the first time astronomers traced a high-energy neutrino back to its source. The shock wasn't just the detection itself, it's that out of thousands of known blazars, only TXS seems capable of this feat. The paradox cuts to the heart of black hole physics. Neutrinos, those ghostly particles barely interacting with matter, typically require extreme conditions to accelerate supernova shockwaves, pulsar winds, or yes, black hole jets. When Ice Cube traced that lone neutrino to TXS's flaring gamma rays, it seemed to confirm blazars as cosmic particle accelerators, except no other blazar, no matter how violent, has ever repeated the trick. Not the monster at M87's core, not the famously erratic OJ287, just this single overachiever in Orion's periphery, flickering with neutrinos like a faulty cosmic light switch. One theory points to TXS's unique buffet. While most blazars dine on garden-variety interstellar gas, this one might be shredding a particularly meaty stellar carcass, a dense molecular cloud, or even a wayward star. As the black hole's jet plows through this debris, proton collisions could spawn pions that decay into both gamma rays, which we see, and neutrinos, which we occasionally catch. Support for this comes from the neutrino's timing. It arrived during a gamma ray flare, suggesting shared origins in a recent cosmic car crash, but there's a catch. TXS isn't the only blazar caught snacking. Others show evidence of tidal disruption events yet produce no detectable neutrinos. This has led to more exotic explanations. Perhaps TXS's jet contains unusually heavy atomic nuclei, which shatter into neutrinos more efficiently when they collide. Or its magnetic fields might be tangled just right to trap protons long enough for multiple collisions, boosting neutrino production like a subatomic pinball machine. The wildest idea, quantum gravity effects near TXS's event horizon could be tweaking neutrino properties, making them slightly more detectable than their cousins from other blazars. The most tantalizing clue lies in the jet structure. Millimeter wave radio maps reveal TXS's outflow isn't smooth but lumpy, with knots of plasma that could act as particle acceleration sites. If one such knot recently crossed a shock front in the jet, it might have briefly turned the entire beam into a neutrino factory. This would explain why the signal hasn't repeated. It was a transient alignment unlikely to recur anytime soon. What makes TXS's neutrino whisper so revolutionary isn't the detection itself, but the questions it leaves hanging. If blazard jets can manufacture neutrinos, why does only one advertise it so blatantly? Are we seeing a rare phase in black hole evolution, or does TXS hold some hidden ingredient others lack? Every new observation deepens the mystery, reminding us that even the most violent objects in the cosmos keep secrets, and sometimes they reveal them one ghostly particle at a time. IGRJ 1709-13624 doesn't just exhale, it hyperventilates. This small but unruly black hole, tucked away in the constellation Scorpius, has been caught ejecting a wind so ferocious it clocks in at 20 million miles per hour, nearly 3% the speed of light. To put that in perspective, if Earth's atmosphere moved at even a fraction of that speed, our planet would be stripped bare in seconds. But here's the real shocker. According to every existing model, IGR's pint-sized gravitational engine shouldn't be capable of such cosmic heavy breathing. The anomaly first came to light in 2011, when NASA Rossi X-ray timing explorer caught strange dips in the black hole's emissions. Instead of the steady flicker typical of feeding black holes, IGR's X-rays plunged abruptly, as if someone kept flipping a cosmic dimmer switch. Follow-up observations revealed the culprit, a supersonic wind of ionized gas blasting outward in erratic bursts, each dense enough to momentarily eclipse the black hole's inner glow. Imagine trying to observe a lighthouse through a sandstorm, where every gust alternately hides and reveals the beam. What makes this wind so baffling is its sheer force relative to the black hole's size. Clocking in at just 5 to 10 solar masses, IGR is a featherweight compared to supermassive giants like M87. Yet its outflow carries enough kinetic energy to rival quasars 1,000,000 times heftier. Standard accretion disk physics can't explain it. The radiation pressure from such a small black hole's meal shouldn't muster the thrust needed to launch gas at these velocities. It's like a garden hose producing the water pressure of a fire hydrant. The math simply doesn't add up. One radical theory points to magnetic tornadoes. Simulations suggest IGR's accretion disk might be threaded with ultra-strong magnetic fields, coiled like springs by the black hole's spin. When these fields snap a process called magnetic reconnection, they could fling surrounding plasma outward like a slingshot. Supporting this, the wind's composition shows unusual ionization states, hinting at extreme magnetic heating. But even this falls short. The required field strengths border on implausible, demanding conditions never observed elsewhere in nature. Then there's the wind's bizarre stop-start rhythm. Unlike the steady jets seen from larger black holes, IGR's outflows arrive in staccato bursts, each lasting mere hours before shutting off completely. Some researchers speculate this could reflect a warped disk wobbling in and out of alignment, like a tilted spinning top that periodically flings material outward. Others wonder if we're seeing evidence of disk seismology, where vibrations in the accretion disk triggered by clumps of infalling matter create pressure waves that eject gas in pulses. The most tantalizing clue lies in the wind's temperature profile. Spectroscopy reveals two distinct velocity components, a slower, warmer layer sheathing an ultrafast core. This structure mirrors shock patterns seen in experimental plasma physics, suggesting the wind might be colliding with itself mid-flight, creating internal shockwaves that further accelerate particles. If confirmed, it would mean IGR's outflow isn't just blowing, it's turbocharging itself through some self-sustaining cosmic feedback loop we've yet to fully map. What makes this ghostly wind so revolutionary isn't just its defiance of expectations, but what it implies about black holes across the mass spectrum. If a run-of-the-mill stellar black hole can muster such extreme behavior, it suggests our theories about accretion and outflow mechanics might be missing a critical piece of the puzzle. Perhaps some hidden efficiency boost that kicks in under specific, still unknown conditions. Every gust from IGRJ 1709-13624 carries a whispered challenge. In the darkness, even the smallest monsters can roar louder than we ever imagined. STRANGEST 1430 plus 2303 doesn't just flicker, it counts down. Nestled in the constellation Boötes, this supermassive black hole has been pulsing with X-rays in a pattern so precise it resembles a cosmic clock ticking toward midnight. Since 2021, astronomers have watched its flares grow brighter and more frequent, their rhythm accelerating like the final spins of a coin before it settles. The chilling implication: we might be witnessing the last orbits of two black holes spiraling toward collision, an event that would shake the fabric of space-time itself. But not everyone's convinced, and the debate reveals just how little we truly understand about the dance of darkness. The case for an impending merger rests on three eerie clues. First, the flare's timing repeating every few hundred days, then speeding up to monthly, then weekly, mirroring the exponential orbital decay predicted as gravitational waves sap energy from circling black holes. Second, the X-ray's spectral fingerprint, showing features consistent with gas trapped between two gravitational titans, squeezed like an accordion with each pass. Third, and most compelling, the system's optical flickers match simulations of a smaller black hole plowing through its partner's accretion disk every orbit, kicking up shockwaves that glow brighter as the gap narrows. It's as if we're watching a cosmic bullseye form in real time, with each flare marking another step toward impact. Skeptics counter with equally persuasive arguments. The claimed orbital period, now down to mere hours, would place the black holes so close that general relativity demands they merge within months. Yet STRANGEST has teased observers for years, its flares arriving late or dimmer than models predict. Some suggest we're seeing not a death spiral, but a sick star. If the black hole's disk hosts a massive, unstable star on an eccentric orbit, its periodic close passes could stir up turbulence, mimicking merger signals without the apocalyptic finale. Others propose a simpler culprit, a wobbling jet. As the black hole's outflow processes like a wobbly top, its beam might periodically point toward Earth, creating the illusion of timed flares. The most damning critique comes from the numbers themselves. To produce gravitational waves strong enough for the observed decay, the secondary black hole would need impossibly high mass unless it's a rare intermediate mass black hole, a class of objects we've scarcely confirmed. Without direct gravitational wave detection impossible with current tech for such distant, massive objects, the merger hypothesis leans heavily on circumstantial evidence. It's the cosmic equivalent of hearing footsteps upstairs and assuming it's a burglar when it might just be the house settling. Yet the stakes couldn't be higher. If STRANGEST black holes do collide, the resulting gravitational waves would dwarf any detected before, carrying clues about how supermassive black holes grow and whether Einstein's laws hold under such extremes. Even the skeptics agree, whether it's a merger, a mirage, or something stranger, STRANGEST 1430 plus 2303 is forcing us to confront the limits of our knowledge. Every flicker from this distant giant asks the same unnerving question: when the cosmos counts down, do we even know how to listen? Black holes seem to follow one simple rule in our universe: go big or stay small. On one end, we've found stellar mass black holes, the collapsed cores of dead stars, weighing in at a few times the mass of our Sun. On the other, supermassive behemoths like Sagittarius A, tipping the scales at millions or even billions of solar masses. But where's the middle child, the cosmic Goldilocks zone between these extremes? Intermediate mass black holes should be everywhere according to theory, yet they're the universe's quietest ghosts, appearing almost reluctant to reveal themselves. The math is clear. If supermassive black holes grow by merging and consuming smaller ones, the cosmos should be littered with stepping stones, black holes in the hundreds or thousands of solar masses. But observations tell a different story. Of the thousands of black holes catalogued, only a handful, like HLX-1 in the galaxy ISO 24349, even hint at this elusive middle class. It's like walking into a forest expecting to find saplings, young trees, and ancient giants, only to discover seedlings and thousand-year-old oaks with nothing in between. So where did they all go? One possibility is camouflage. Intermediate black holes might be hiding in plain sight, disguised as something else. Take the globular cluster Omega Centauri, a dense swarm of stars orbiting the Milky Way. Its core moves with a peculiar gravitational sway, as if something hefty lurks there. Estimates suggest a black hole around 40,000 solar masses could explain the motion, but direct evidence remains frustratingly out of reach. These objects might not have the glowing accretion disks of their supermassive cousins, instead drifting in near darkness, only betraying their presence through subtle tugs on nearby stars. Another theory points to a violent adolescence. Intermediate black holes could be fleeting, swallowed too quickly by larger neighbors to leave a lasting mark. In crowded galactic centers, mergers might happen so fast that mid-sized black holes are rare, not because they don't form, but because they're promptly devoured. Imagine a cosmic game of Pac-Man, where the middleweights are always just one wrong move away from being erased from the board, but the most tantalizing explanation. We've been listening wrong. Traditional detection methods hunting for X-rays from hot gas or tracking star motions might miss black holes in less obvious environments. Some could be drifting in the voids between galaxies where there's little material to attract or heat up. Others might form in ways that leave no traditional signature, like direct collapse in the early universe, skipping the stellar mass stage entirely. It's a humbling reminder. Sometimes the universe doesn't hide its secrets, we just haven't learned how to look for them yet. The search isn't just academic. Finding these missing links would solve a cosmic chicken and egg problem. Did supermassive black holes grow from smaller seeds, or were they born giant? Each undetected intermediate black hole leaves that question hanging. But with new tools like gravitational wave astronomy and next-generation telescopes, we might finally be closing in on the universe's quietest giants and rewriting the story of how darkness grows. Some galaxies play by the rules. NGC 1277 laughs at them. This compact lenticular galaxy, 220 million light-years away in Perseus, hosts a supermassive black hole so disproportionately large it defies every scaling law astronomers use to predict black hole growth. At 17 billion solar masses, its behemoth accounts for nearly 60% of the galaxy's bulge mass, 10 times heavier than models allow. It's the cosmic equivalent of finding a toddler bench pressing a pickup truck. But the real mystery isn't just the black hole's impossible size, it's the invisible scaffolding that must be holding this lopsided system together. Dark matter. The universe's ghostly gravitational glue typically forms halos around galaxies, their weight dictating how stars and gas move. Yet NGC 1277's dark matter halo appears suspiciously anemic compared to its monstrous central singularity. Most galaxies this size would have a dark matter halo 30 times more massive than their stars. Here, the ratio barely reaches 3:1. This cosmic accounting error suggests one of two radical possibilities. Either dark matter behaves in ways we've never observed, or this black hole grew through channels that bypass normal astrophysical pathways entirely. The first clue lies in the galaxy's star formation, or rather, its absence. Unlike spiral galaxies constantly birthing new stars, NGC 1277's stellar population is ancient and quiescent, with no signs of recent mergers that could explain the black hole's inflated size. This eliminates the conventional explanation that multiple black holes merged over time, snowballing into a singular giant. Instead, the black hole might have formed through direct collapse in the early universe, bypassing the stellar mass stage entirely. Imagine skipping the sapling phase and sprouting a full-grown redwood overnight. That's the scale of anomaly we're dealing with. Then there's the dark matter distribution. Most galaxies show a smooth, extended halo, but NGC 1277's appears truncated, as if someone took cosmic scissors and snipped away its outer edges. Some theorists propose an ancient collision stripped away much of its dark matter, leaving behind a dense central core that somehow funneled an absurd amount of material into the black hole. Others float an even wilder idea, that the black hole itself altered the dark matter's behavior, its extreme gravity somehow pushing the halo outward like a boat, creating ripples in water. The most tantalizing data comes from the galaxy's globular clusters. These dense star swarms typically orbit in a spherical distribution, tracing the dark matter halo's shape. Here, they're bizarrely concentrated near the galaxy's core, their orbits suggesting they're dancing to the tune of the black hole's gravity rather than the halo's. It's as if the black hole isn't just a tenant in this galactic house, it's the foundation, the walls, and the roof all at once. What makes NGC 1277 revolutionary isn't just its defiance of rules, it's the questions it forces us to confront. Do black holes and dark matter interact in ways we've never imagined? Could some supermassive black holes be primordial relics from the universe's first seconds that seeded galaxy formation rather than the other way around? Every new observation peels back another layer of this cosmic onion, revealing just how much we still don't understand about the silent, invisible forces sculpting our universe. And somewhere in that darkness, NGC 1277's oversized heart beats on a gravitational rebel, rewriting the rules one impossible measurement at a time. GRS 1915 plus 105 doesn't just misbehave, it flaunts its chaos like a cosmic rebel without a cause. This black hole, 11,000 light-years away in Aquila, erupts in X-ray tantrums so violent they've been nicknamed heartbeat and plateau states, flickering between fury and eerie calm like a possessed strobe light. But beneath the drama lies a far deeper controversy. Some theorists argue its antics suggest the unthinkable, a singularity stripped bare, its event horizon missing entirely. If true, it would violate one of general relativity's sacred tenets, that singularities must always hide behind the point of no return. The case rests on GRS's most infamous outburst, sudden X-ray shutoffs where emissions drop by a factor of 100 in minutes, as if someone yanked the cosmic power cord. In normal black holes, such dips occur when the inner accretion disk gets drained, but here's the twist. The energy spectra during these blackouts match no known disk model. Instead, they resemble matter evaporating mid-plunge, as if particles vanish before reaching the theorized event horizon. It's like watching a diver leap off a cliff, only to dissolve in midair before hitting the water. One radical interpretation, the event horizon might be porous or absent altogether. In standard physics, a singularity without its cloak of darkness would unleash a firestorm of contradictions, from infinite gravity at its core to naked causality violations. Yet GRS's heartbeat states regular X-ray pulses every 50 seconds, mirror simulations of a naked singularity's predicted oscillations. Imagine poking a rubber membrane and watching it vibrate. Now replace the membrane with space-time and the finger with a singularity bare to the cosmos. That's the shudder some researchers think they're seeing encoded in those X-ray beats. Skeptics counter with less earth-shattering explanations. The dips might trace to a warped disk processing like a wobbly top, periodically eclipsing our view of the inner turmoil. Or perhaps JRS's extreme spin, near light speed, stretches the event horizon so thin that matter skims its surface like a stone skipping a lake, creating illusions of premature evaporation. Even the heartbeat could stem from ordinary instabilities, like a faucet dripping at relativistic speeds, but the plot thickens with JRS's hysteresis patterns, where X-ray brightness follows different paths on its way up and down, a hysteresis loop normally seen in magnetic systems, not gravity wells. This has sparked wilder theories: quantum gravity effects warping the singularity's neighborhood, or extra dimensions pinching space-time into knots that mimic horizonless behavior. The stakes: if JRS 1915 plus 105 truly lacks an event horizon, it wouldn't just break Einstein's rules, it would demand new physics to explain how reality stitches itself together at gravity's edge. Until we peer closer, perhaps with next-gen X-ray polarimeters or gravitational wave detectors tuned to high frequencies, this rogue black hole will keep taunting us with the ultimate cosmic taboo, a monster that refuses to wear its mask. The universe loves a good magic trick, and Q2237 plus 0305 might be its most baffling illusion yet. This supermassive black hole, parked directly between Earth and a brilliant quasar 8 billion light-years away, should be invisible. Instead, it announces its presence by warping the quasar's light into 4 perfect images, a cosmic mirage so precise it's nicknamed the Einstein Cross. Yet hidden in those symmetrical splinters of light lies a glitch in the matrix, subtle distortions that even Einstein's masterpiece can't fully explain. At first glance, the cross seems like textbook gravitational lensing. The black hole's immense gravity bends space-time like a funhouse mirror, splitting the quasar's light into multiple paths as it journeys toward us. But zoom in closer and anomalies emerge. The 4 quasar images flicker out of sync, sometimes by days, other times by weeks, as if the black hole isn't just bending light but selectively stalling it. Even stranger, spectral lines in the quasar's light appear duplicated at slightly shifted wavelengths, like a musical chord played a half-step out of tune. General relativity predicts some variability, but not these specific, stubborn discrepancies. One theory points to hidden structures near the black hole's event horizon. If dense knots of dark matter or a swarm of rogue planets orbit close enough, their combined gravity could tweak the lensing effect like fingerprints smudging a lens. Others suggest more radical physics, perhaps quantum fluctuations in space-time's fabric at microscopic scales, magnified by the black hole's gravitational might. Imagine a hall of mirrors where some reflections warp slightly because the mirrors themselves aren't perfectly smooth. Then there's the matter of missing mass. To produce the Einstein Cross's near-perfect symmetry, the black hole's host galaxy should contribute noticeable gravity, yet observations show its visible stars account for less than half the required mass. The rest, possibly an enshrouding halo of primordial black holes, or even an exotic form of dark matter that interacts with light in ways we've never seen. The most tantalizing clue lies in the flicker patterns. In 2019, one quasar image brightened dramatically while its counterparts remained stable, a disparity lasting months. Conventional lensing models can't easily explain such prolonged, isolated brightening unless the black hole's immediate environment is far more turbulent than assumed. Some researchers speculate we're seeing light scrape past the photon sphere, the point where gravity bends light into perfect orbits before barely escaping. It's like watching a daredevil skid along a cliff's edge, each near miss amplifying the drama. What makes Q2237 plus 0305 so revolutionary isn't just its defiance of models, it's the precision with which it exposes our blind spots. Every anomalous flicker, every spectral mismatch is a breadcrumb leading toward deeper questions. Is dark matter clumpier than we thought? Does space-time have texture at tiny scales? Or are we glimpsing hints of gravity's quantum nature, written in light stretched across billions of years? The cross keeps its secrets for now, but with each observation, it's as if the universe leans closer, whispering, "Look again." The trick isn't finished yet. From the eerie clockwork heartbeat of GSN 069 to the drunken cosmic stagger of H174332's jet, each of these 25 signals forces us to rewrite the rules of physics. Black holes weren't supposed to flicker like broken streetlights or whisper in infrared. They weren't meant to vanish their own jets, spit out neutrinos like cosmic bullets, or leave fingerprints on light itself. Yet here we are, staring at the data, proof that the universe's darkest corners are far stranger than our boldest theories predicted. Take the phantom echoes of V404 Cygni, screaming into the void only to hear its own voice bounce back from nowhere. Or GW190521, the gravitational wave that brought us a black hole that shouldn't exist. Even the quiet ones like Assassin 14, Lie's infrared glow, or the ghostly wind of IGRJ 17091 refused to play by the cosmic rulebook. These aren't just anomalies, they're breadcrumbs leading us toward truths we haven't even imagined yet. Physics thrives at its breaking points and black holes. They're the ultimate wrecking balls, so now it's your turn. Which signal leaves you staring at the night sky with more questions than answers? The neutrino blazing blazar TXS 0506. The naked singularity tease of Jaris 1915. Or maybe the Einstein crosses light-bending riddles. Drop your thoughts in the comments. Let's dissect these cosmic paradoxes together. And if you're hungry for more mysteries, hit subscribe. The universe isn't done surprising us, and neither are we. The next breakthrough could be just one signal away, ready to shatter everything we thought we knew.